Nomenclature systems of carbon compounds. System of common names. We have seen that today millions of carbon compounds are known. Initially, when the number of known carbon compounds was small, scientists named them in a variety of ways. Now those names are called as common names. For example, the source of the names of the first four alkanes, namely methane, ethane, propane and butane, are different. The names of alkanes thereafter were given from the number of carbon atoms in them. Two isomeric compounds having a straight chain or branched chain in their structural formula are possible for the molecular formula C4H10. The difference and the interrelationship in them was indicated by naming them as N-butane, that is normal butane, and I-butane, that is isobutane. Understood, children? As the time progressed, the carbon compounds became very large in number and their common name caused confusion. A need was felt to have a logical system acceptable to all for naming the carbon compounds. International Union for Pure and Applied Chemistry put forth a nomenclature system based on the structure of the components, and it was accepted all over the world. There is a provision in this system for giving a unique name to all the carbon compounds. Let us see how some straight chain compounds containing one functional groups are given IUPAC names, and let us also see their common names. There are three units in the IUPAC name of any carbon compound: parent, suffix and prefix. These are arranged in the names as follows: prefix, parent and suffix. An IUPAC name is given to a compound on the basis of the name of its parent alkane. The name of the compound is constructed by attaching appropriate suffix and prefix to the name of the parent alkane. The steps in the Iupac nomenclature of straight chain compounds are as follows. Step 1. Draw the structural formula of the straight chain compounds and count the number of carbon atoms in it. The alkane with the same number of carbon atoms is the parent alkane of the concerned compound. Write the name of this alkane. In case of carbon chain of the concerned compound contains a double bond, change the ending of the parent name from "-ene" to "-ene". If the carbon chain in the concerned compound contains a triple bond, change the ending of the parent name from "-ene" to "-ine". Now children, see this table. Here the structural formula is CH3CH2CH3, where the straight chain we have C bond C bond C. So the parent name here is propane. Structural formula CH3CH2OH. So the chain is C bond C and parent name ethane. Structural formula CH3CH2COOH. So it is a straight chain C bond C bond C. Parent name we have propane. Next, CH3CH2CH2CHO. Straight chain we have C bond C bond C bond C, and the parent name is butane. Next one, structural formula CH3CH double bond CH2. Straight chain C bond C double bond C. So here the parent name is propene. CH3 bond C triple bond CH. Straight chain we have C bond C, triple bond C. So the parent name here is propyne. Got it, children? Step 2. If the structural formula contains a functional group, replace the last letter E from the parent name by the condensed name of the functional group as the suffix. Exception: the condensed name of the functional group halogen is always attached as the prefix. Step 3. Number the carbon atoms in the carbon chain from one end to the other. Assign the number 1 to the carbon in the functional group CHO or COOH if present. Otherwise, the change can be numbered in two directions. Accept the numbering which gives smaller number to the carbon carrying the functional group. In the final name, a digit or number and a character, that is letter, should be separated by a small horizontal line. Usually, numbering is not required if carbon chain contains only 2 carbon atoms. Now look here. The table has the structural formula CH2OH. Functional group is OH, that is all. Parent name ethane. Parent suffix ethanol. Second, structural formula CH3CH2Cl. Functional group Cl, that is chloro, and parent name we have ethane. And prefix parent we have chloroethane. Third, BrCH2CH3. Functional group Br bromo, and parent name we have ethane, and prefix parent we have bromoethane. Next, CH3CH2CHO. Functional group CHO, that is all. Parent name propane. Parent suffix propanol. Next, CH3COOH. Functional group COOH, that is oic acid. Parent name ethane and parent suffix ethanoic acid. Next, CH3NH2. Functional group NH2, that is amine. Parent name methane and parent suffix methanamine. Next, CH3COCH3. Functional group we have CO1. Parent name propane and parent suffix propanol. Next, here the structural formula is CH3CHOHCH3, where we have two numberings of the carbon chain and acceptable numbering. Both the numberings are equivalent, and Iupac name is propane to all. Second, structural formula CH3CH2 CH2CHClCH3. The numbering of the carbon chain and acceptable numberings are given. And the Iupac name of the compound is 2-chloropentane. Next structural formula is CH3C double bond O CH2 CH2 CH3. Two numberings of the carbon chain and acceptable numberings are shown, and the Iupac name of the compound is pentane 2,1. Some more steps are required for writing Iupac names of compounds having more complex structural units such as branch chains, carbon rings, heterocyclic, etc. Study of these will be included in further standards. At the same time, also keep in mind that there is a practice of using common names of carbon compound which are frequently used in the laboratory. Now look here at this table. We have common name, their structural formula and IUPAC name. So the first name we need to write is ethylene. Now the structural formula is CH2 double bond CH2. So the IUPAC name is ethene. Acetylene, CH triple bond CH. IUPAC name ethyne. Acetic acid, CH3 bond COOH. Ethanoic acid. Methyl alcohol, CH3OH. Methanol. Ethyl alcohol, structural formula is CH3CH2OH and IUPAC name ethanol. Acetaldehyde, CH3CHO, ethanol. Next, acetone, CH3COCH3, propanol. Next, ethyl methyl ketone, CH3COCH2CH3, butane 2,1. Ethylamine, CH3CH2NH2. Ethanamine is the IUPAC name. And next, N-propyl chloride, CH3CHCl2Cl, 1-chloropropane. Okay, children? Next is combustion. Let us first look at combustion as a chemical property of carbon compounds. We have seen in a previous standard that carbon in the form of various allotropes on ignition in the presence of oxygen undergoes combustion to emit heat and light and forms carbon dioxide. Hydrocarbons as well as most of the carbon compounds undergoes combustion in the presence of oxygen to emit heat and light and form carbon dioxide and water as the common products. Some of the combustion reactions are as follows. Carbon plus oxygen gives CO2 plus heat plus light. CH4, that is methane, plus 2O2 gives us CO2 plus 2H2O plus heat and light. Third, CH3CH2OH, that is ethanol, plus 3O2 gives us 2CO2 plus 3H2O plus heat plus light. Okay? Now children, try this. Apparatus we require is a Bunsen burner, copper gauze, metal plate, etc. Chemicals required are ethanol, acetic acid and naphthalene. Procedure. Place one of the above chemicals, 3 to 4 drops or a pinch, on a clean copper gauze at the room temperature. Hold it on a blue flame of the Bunsen burner and then observe. Is the smoke or the soot seen to form due to combustion? Hold the metal plate on the flame when the substance is undergoing combustion. Does any deposit get collected on the plate? Which color? Repeat the same procedure during using the other chemicals from the above list. In the above activity, ethanol is a saturated compound, while naphthalene is an unsaturated compound. Generally, saturated carbon compounds burn with a clean blue flame, while unsaturated carbon compounds burn with a yellow flame and release black smoke. It is this black smoke due to which a deposit of black soot got collected on the metal plate. Comparison of molecular formulae indicates that the proportion of carbon is larger in unsaturated components than in saturated compounds. As a result, some unburnt carbon particles are also formed during combustion of unsaturated compounds. While in the flame, these hot carbon particles emit yellow lights and therefore the flame appears yellow. However, if oxygen is limited, a yellow flame is obtained by combustion of saturated compounds as well. Now again try this. Light a Bunsen burner. Open and close the air hole at the bottom of the burner by means of a movable ring around it. When do you get yellow sooty flame? And when do you get a blue flame? We get yellow sooty flame when the air hole at the bottom is closed, while blue flame is obtained when the air hole at the bottom is open. Children, always remember, there are inlets for air in the gas or kerosene stove at home. It is because of these air inlets that the gaseous fuel is mixed with sufficient oxygen and a clean blue flame is obtained. In case there is deposition of black soot on the bottom of cooking vessel, it is an indication of choking of air inlets and thereby wastage of fuel. In such case, the air inlets of stove should be got cleaned. Understood, children? Good. Now you have seen that carbon compounds start burning by combining easily with oxygen in the air when ignited in the air. In this process of combustion, all the chemical bonds in the molecules of the carbon compound break and CO2 and H2O are formed as the products. In other words, the carbon compounds are completely oxidized during combustion. Chemical compounds can also be used as source of oxygen. Substances that can give oxygen to other substances are called oxidant or oxidizing agents. Potassium permanganate or potassium dichromate are commonly used as oxidizing agents. An oxidizing agent effects on certain functional groups in present carbon compound. Try this, children. Apparatus, test tube, Bunsen burner, measuring cylinder, dropper, etc. Chemicals required are ethanol, dilute solution of sodium carbonate, dilute solution of potassium permanganate. Procedure. Take 2 to 3 ml ethanol in a test tube. Add 5 ml of sodium carbonate solution to it and warm the mixture by holding the test tube on the burner for a while. Do the drop-wise addition of a dilute solution of potassium permanganate to this warm mixture with stirring. Does the typical pink color of potassium permanganate stay as it is on addition? No, it does not. Does the pink color stop vanishing and stays on after some time of the addition process? Yes, stops vanishing. In the above activity, ethanol gets oxidized by acidic potassium permanganate to form ethanoic acid. Only certain bonds in the vicinity of the functional group takes part in this reaction. The following equation will explain this. CH3CH2 ethanol gives us CH3C double bond OOH, that is ethanoic acid. Now compare how it is the transformation of ethanol into ethanoic acid and oxidation reaction. On adding the pink colored solution of potassium permanganate to ethanol, the pink color disappears in the beginning. This is because potassium permanganate is used up in the oxidation reaction. At a certain point of the addition, oxidation of all the quantity of ethanol in the test tube is complete. If the addition of potassium permanganate is continued beyond this point, it is not used up and become excess. The pink color of this excess potassium permanganate does not vanish but stays as it is. Understood, children? Okay. Now try this. Apparatus, test tubes, droppers, etc. Chemicals are tincture iodine, bromine water, liquefied vanaspati ghee, various vegetables oil, peanut, safflower, sunflower, olive, etc. Now take 4 ml of oil in a test tube and add 4 drops of tincture iodine or bromine water in it. Shake the test tube. Find out whether the original color of bromine or iodine disappears or not. Repeat the same procedure using other oils and vanaspati ghee. In the above activity, the observation of disappearing or diminishing color of bromine or iodine indicates that bromine or iodine is used up. This means that bromine or iodine has undergone a reaction with the concerned substance. So this reaction is an addition reaction. When a carbon compound combines with another carbon to form a product that contains all the atoms in both the reactant, it is called as an addition reaction. Unsaturated compounds contain a multiple bond as their functional group. They undergo addition reaction to form a saturated compound as the product. The addition reaction of an unsaturated compound with iodine or bromine takes place instantly at room temperature. Moreover, the color change can be felt by eyes. Therefore, this reaction is used as a test for detection of a multiple bond in a carbon compound. In the above activity, the color of iodine or bromine disappears in the reaction between an oil and iodine. However, there is no color change with vanaspati ghee. What inference will you draw from this? Which of the substances do contain a multiple bond? Now look here in this table, children. We have stearic acid with molecular formula C17H35COOH. Number of carbon double bonds 0, and will it decolorize? No. Oleic acid C17H33COOH. Number of carbon double bonds 1, and will it decolorize iodine? Yes. Palmitic acid C15H31COOH. There is no carbon double bond and it will not decolorize. Linoleic acid C15H31COOH has 2 double carbon bonds and it will decolorize iodine. The unsaturated compound can also undergo addition reaction with hydrogen to form a saturated compound. However, it is necessary to use a catalyst like platinum or nickel for this reaction. We have already seen that catalyst is such a substance due to presence of which the rate of reaction changes without causing any disturbance to it. Ethene on hydrogenation with the catalyst platinum or nickel gives ethane. This reaction is used for hydrogenation of vegetable oils in presence of nickel catalyst. You have seen in the above activity that iodine test indicates presence of multiple bonds in the molecules of oils, while Vanaspati ghee is found to be saturated. This molecule of vegetable oil contains long and unsaturated carbon chain. Hydrogenation transforms them into saturated chains and thereby Vanaspati ghee is formed. Unsaturated fats containing double bonds are healthy, while saturated fats are harmful to health. Understood, children? Okay. As the single bonds CH and CC are very strong, the saturated hydrocarbons are not reactive and therefore they remain inert in the presence of most reagents. However, saturated hydrocarbons in presence of sunlight react rapidly with chlorine. In this reaction, chlorine atoms replaces one by one all the hydrogen atoms in the saturated hydrocarbon. The reaction in which the place of one type of atom or group in a reactant is taken by another atom or group of atom is called as substitution reaction. Chlorination of methane is a substitution reaction which gives four products. CHCl2 in the presence of sunlight gives CH3Cl plus HCl. CH3Cl plus Cl2 in the presence of sunlight gives CH2Cl2 plus HCl. CH2Cl2 plus Cl2 in the presence of sunlight gives CHCl3 plus HCl. CHCl3 plus Cl2 in the presence of sunlight gives CCl4 plus HCl. Understood? Still larger number of products are formed in chlorination reaction of higher homologous of alkanes. Use your brain power. In the chlorination substitution reaction of propane, two isomeric products containing one chlorine atom are obtained. Draw their structural formulae and give their Iupac names. Chlorination of propane results in the formation of mixture of two isomers, chloropropane and 2-chloropropane. Here are the structural formula of both. Understood, children? Let's move ahead now. Ethanol and ethanoic acids are two of the commercially important carbon compounds. Let us now learn more about them. At room temperature, colorless ethanol is a liquid and its boiling point is 78 degrees Celsius. Generally, ethanol is called alcohol or spirit. Ethanol is soluble in water in all proportions. When aqueous solution of ethanol is tested with litmus paper, it is found to be neutral. Consumption of small quantities of dilute ethanol shows its effect. Even though it is condemned, still it remains socially widespread practice. Consumption of alcohol harms health in a number of ways. It adversely affects the physiological process and the central nervous system. Consumption of even a small quantity of pure alcohol, called absolute alcohol, can be lethal. Ethanol being good solvent, it is used in medicines such as tincture iodine, that is solution of iodine and ethanol, cough mixture, and also in many tonics. Now let's move ahead. You have learnt about the oxidation reaction of ethanol in the previous unit. Two more reactions of ethanol are as follows. The functional group OH plays an important role in the reaction of ethanol. Reaction with sodium. 2Na plus 2CH3 CH2OH gives 2CH3 CH2ONA plus H2, that is sodium ethoxide. All the alcohols react with sodium metal to liberate hydrogen gas and form sodium alkoxide salts. In the reaction of ethanol with sodium metal, hydrogen gas and sodium ethanoic are formed as product. Try this, children. This activity should be done carefully. The apparatus required: big test tube, delivery tube fitted in a rubber cork, knife, candle, etc. Sodium metal, ethanol, magnesium, ribbon, etc. are the chemicals used. Now what is the procedure? Take 10 ml of ethanol in a big test tube. Cut sodium metal into 2 to 3 pieces of a cereal grain size. Put the sodium pieces into ethanol in the test tube and fix the gas delivery tube to the test tube. Take a burning candle near the outlet of the gas delivery tube and observe. Which is the combustible gas coming out of the gas delivery tube? We can see hydrogen gas coming out of the gas delivery tube. Why do sodium pieces appear to dance on the surface of ethanol? Sodium, being highly reactive metal, appears to dance on the surface of ethanol. Repeat the above procedure using magnesium ribbon instead of sodium. Do you see the gas bubble released from the piece of magnesium ribbon? Yes, we can see gas bubble released from the piece of magnesium ribbon. Does the magnesium metal react with ethanol? Yes, it does. Understood? In the previous standard, you have learned that a moderately reactive metal such as magnesium reacts with strong acid to liberate hydrogen gas. Though ethanol is neutral, it reacts with sodium metal and liberates hydrogen gas. Sodium, being highly reactive metal, it reacts with the neutral functional group OH of ethanol. Let's move ahead now. When ethanol is heated at the temperature 170 degrees Celsius with excess amount of concentrated sulfuric acid, one molecule of water is removed from its molecule to form ethene, an unsaturated compound. CH3, CH2OH. In the presence of concentrated sulfuric acid at 170 degrees Celsius gives CH2 double bond CH2, that is ethene, plus H2O. Here the concentrated sulfuric acid acts as a dehydrating agent. Okay? Science. Alcohol, a fuel. The sugarcane plant transforms solar energy into chemical energy very efficiently. When molasses obtained during production of sugar from sugarcane is subjected to fermentation, alcohol, that is ethanol, is obtained. On combustion in sufficient air, ethanol gives carbon dioxide and water as the only product. In this way, ethanol is a clean fuel. Therefore, in some countries, it is used as an additive to increase the efficiency of petrol, Such a fuel is called gasohole. Ethanoic acid. It is a colorless liquid with boiling point 118 degrees Celsius. Ethanoic acid is commonly known as acetic acid. Its aqueous solution is acidic and turns blue litmus red. Vinegar, which is used as preservative in pickles, is a 5 to 8% aqueous solution of acetic acid. The melting point of pure ethanoic acid is 17 degrees Celsius. Therefore, during winter in cold countries, ethanoic acid freezes at room temperature itself and looks like ice. Therefore, it is named glacial acetic acid. Understood, children? Good. Now let's proceed further. Apparatus required here are glaze tile, glass rods, pH paper, blue litmus paper. Chemicals required are dilute ethanoic acid and dilute hydrochloric acid. Procedure: place 2 strips of blue litmus paper on a glazed tile. Put 1 drop of dilute hydrochloric acid on one strip with the help of a glass rod. Put 1 drop of dilute ethanoic acid with the help of another glass rod on the other strip. Note the color change taken in the litmus strip. Repeat the same procedure using strips of pH paper. Now what do we observe? Testing ethanoic acid and hydrochloric acid. Substance ethanoic acid. The color change is red. So it is less than 7. So the color change seen on the pH paper is yellow and corresponding pH is 3. Hydrochloric acid. It changed to red. So it is less than 7. So the color change here is red and corresponding pH is 1. Got it? Good. Now the chemical properties of ethanoic acid. So ethanoic acid contains carboxylic acid as its functional group. The chemical reaction of ethanoic acids are mainly due to this functional group. Reaction with base. A reaction with a strong base. Ethanoic acid gives neutralization reaction with a strong base sodium hydroxide to form salt and water. CH3COOH, that is acid, plus NaOH, that is base, gives CH3COONA, that is salt, plus H2O, water. The IUPAC name of the salt formed here is sodium ethanoate, while its common name is sodium acetate. You have learnt in the previous standard that acetic acid is a weak acid. Now reaction with carbonate and bicarbonate. Apparatus required are big test tube, small test tube, bent gas delivery tube, rubber cork, Thiestel funnel, stand, etc. Chemicals are acetic acid, sodium carbonate powder, freshly prepared lime water. Procedure: arrange the apparatus as shown here. Place sodium carbonate powder in the big test tube. Pour 10 ml acetic acid through the Thiestel funnel. Observe the changes taking place in these two test tubes. Which gas does come out as effervescence in the big test tube? Carbon dioxide gas comes out as effervescence in the big test tube. Why are bubbles seen in the small test tube? Carbon dioxide gas formed passes through the delivery tube and enters the small test tube. hence bubble seen in the small test tube. What is the color change in the lime water? The lime water turns milky. Okay? In this activity, ethanoic acid reacts with the basic salt, namely sodium carbonate, to form a salt named sodium ethanoate, water and carbon dioxide gas. 2CH3COOH, that is aqueous, plus Na2CO3 gas gives us 2CH3COONA plus H2O plus CO2. The CO2 gas of the effervescence passes through the gas delivery tube and reacts with the lime water in the small test tube. Lime water turning milky is the test of carbon dioxide gas. If sodium bicarbonate is used instead of sodium carbonate in the above activity, similar observations are obtained. CHCOOH plus NaHCO3 gives CH3COONA plus H2O plus CO2. Now the next. Substances having ester as the functional group are formed by a reaction between a carboxylic acid and an alcohol. Try this, children. Apparatus required: test tube, beakers, burner, etc. Chemicals require: glacial acetic ethanoic acid, ethanol, concentrated sulfuric acid, etc. Procedure: take 1 ml ethanol and 1 ml glacial ethanoic acid in a test tube. Add few drops of concentrated sulfuric acid in it. Keep this test tube in the beaker containing hot water for 5 minutes. Take 20 to 30 ml of water in another beaker and pour the above reaction mixture in it and smell it. Ethanoic acid reacts with ethanol in presence of an acid, catalyst and ester. Ethyl ethanoate is formed. CH3COOH, ethanoic acid, plus CH3CH2OH, that is ethanol, gives us, in the presence of acid and catalyst, CH3COOCH2CH3, ethyl ethanoate, plus H2O, that is water. Are you getting me, children? Okay, good. Now esters have sweet odor. Majority of fruits owe their odor to a particular ester present in them. Esters are used for making fragrances and flavoring. When an ester is reacted with the alkali sodium hydroxide, the corresponding alcohol and carboxylic acid are obtained back. This reaction is called saponification reaction, as it is used for preparation of soaps from fats. Ester plus sodium hydroxide gives sodium carboxylate and alcohol. Understood, children? So, with this we have finished our lesson number 9, carbon compounds. I hope, children, you all have understood all the concepts related to this lesson. Kindly watch the video attentively and please read the lesson for better understanding. So, children, take care of yourself and your family. Thank you, students.